Greetings, everyone. I'm extremely delighted to be here at Neo4j Notes 2025 to share a topic that sits like right at the crossroad of structure and intelligence, that is adaptive knowledge graphs for dynamic RAG systems. So let's get started. So over the last year, retrieval augmented generation or RAG has become one of the most exciting methods for making large language models more accurate and grounded. But as powerful as RAG is, many systems still rely on static and fragmented knowledge. And that's exactly where the story of adaptive KGs or knowledge graphs begins. So, RAG in simple terms means helping a language model look up information before answering. Instead of relying only on what it learned during pre-training, the model retrieves external data from a knowledge source, often a document store or vector database, and then generates a response based on that evidence. So, this approach dramatically reduces hallucinations, improves factual accuracy, and allows LLMs to stay relevant in fast-moving domains like finance, healthcare, and technology. However, the most organizations implement RAG, they have limitations. So traditional RAG pipelines depend on vector databases filled with text chunks that have been transformed into embeddings. When a question arrives, the system retrieves the most similar chunks of text based on semantic similarity. That works beautifully for single document lookups, but it struggles when a question requires reasoning over multiple sources. For instance, let's consider a query like which companies founded by ex Google employees have recently raised funding? So, this question requires the system to connect people, organizations, and events. So, purely embedding based retrieval can't easily make these multi hop connections. So the problem goes deeper. Document-centric data is inherently static. So once you embed it, it stays frozen in that state until you rebuild the index. So as the world changes, your AI doesn't. Business leaders quickly notice that the assistant misses recent updates, gives outdated answers, or fails to show how it reached a conclusion. So traditional rack systems, though practical, they are like filing cabinets of information excellent for storage, but poor at showing relationships and semantic connectivity. So this is where knowledge graphs enter the picture. So just to give an introduction, a knowledge graph represents data as interconnected nodes and relationships rather than just isolated text. Each node might represent a person, a company, or a product, and each edge defines how those entities relate, like founded, works for, acquired, and so on. So instead of searching through disconnected documents, a system can now traverse meaning, moving from one fact to another in a logical, explainable way. So it's not just retrieving information, it's reasoning over it. So imagine this, on one hand, a traditional RAG system with an LLM and a vector database, fast but flat. On the other hand, a graph enhanced RAG system where the LLM interacts with a Neo4j graph that connects facts dynamically. So the difference is actually very profound. The first retrieves fragments, the second retrieves context. And in the first case, it depends on completely static snapshots. The second adapts in real time. So, to set the stage for the rest of this session, static RAG systems are like encyclopedias. They are accurate but frozen in time. Adaptive KGs are more like living brains. They evolve, grow, and connect ideas as new data arrives. So, over the next few minutes, we'll explore how Neo4j enables this adaptivity, allowing our RAG systems to stay fresh, connected, and continuously intelligent. So, what are adaptive KGs indeed? So, let's start with a quick question. What happens when your AI assistant is asked something about a breaking event? like a new product launch, a merger, or regulatory change. Can your system handle that right now, not hours later? So that's where adaptive cages come in. They are not static structures refreshed weekly. They inject and update data continuously, making facts available instantly to downstream AI. So think of them as living knowledge bases that evolve alongside your data. This real time freshness keeps your RAG pipeline sharp and responsive. So, what exactly makes a knowledge graph adaptive? So, at its core, it auto updates when new data arrives. No need for manual reindexing. Nodes and relationships evolve in real time. Also, there is no delay between ingestion and reasoning. So, your AI stays in sync with the world. So, let's take a beat. Most static systems require batch jobs or manual refreshes to reflect change. Adaptive KGs eliminate that. The data is ready before the next query hits. So, one of the biggest advantages is incremental updates. You don't need to rebuild the graph to capture a single new relationship. Say, a relationship complies with or merged with edge. It just updates. So there is no downtime and there is no reprocessing. So here's an analogy that sticks. A static KG is like a printed road atlas, accurate when printed but immediately aging. An adaptive KG is like you could say it's like live GPS with traffic updates, always routing based on current conditions. So let's go a step further. Adaptive KGs also blend semantic and symbolic reasoning. On one side, you have embeddings, which understand meaning even if the phrasing varies. On the other, graph relationships, clean, traceable, and queryable paths. So together, they let AI systems move from fuzzy matching to precise multi-hop logic. And this is what something you called hybrid retrieval, where you have both the embeddings-based retrieval and also a graph-based retrieval. So, for example, consider the question who mentored the founder of the company that just IPO'd? That's two or more hops. So, embeddings may help identify relevance, but it's the graph traversal that connects the dots. Like it helps you reason over multiple nodes and relationships. Okay, so want a real world view? Let's go ahead and do that. A financial AI assistant sees a merger headline like Alpha Corp merges with Beta Inc. The graph auto creates new nodes. It forms the merged with relationship, existing financial updates, and the event text is embedded and linked. So now a user asks, how will the merger affect their market share in Europe? The system retrieves relevant documents via semantic search, traverses ownership paths via graph, calculates a structured answer grounded in current interconnected facts. So that's the magic of an adaptive KG. It doesn't just store, it integrates, relates, and immediately applies new knowledge. So let's walk through how an adaptive knowledge graph works in a real world biomedical setting. Uh, so, since biomedical can be a very good example for creating knowledge graphs, especially when powered by a real-time graph database like Neo4j. So, let's consider the question, what are the treatment options for acute myeloid leukemia in elderly patients? So, at first glance, it seems direct, but answering it well demands much more, like current research, age specific protocols, safety profiles, and how they interrelate. So, this is exactly where Neo4j driven adaptive KGs shine. Let's walk through the example steps that would be required. So, first, we extract medical entities. The system begins by parsing the question using an LLM to identify key medical terms like acute myeloid leukemia, treatment options, and elderly patients. So each of these becomes a node in the Neo4j graph. These anchor points represent the key concepts we'll reason over. So the next step, for each node, live retrieval is triggered from trusted biomedical sources such as PubMed database, clinical guidelines, or trials-based databases. So LLMs summarize the results into clean, interpretable descriptions, which are stored as properties of each node in the Neo4j graph. So these summaries act as contextual metadata for reasoning. Next, we infer edges between nodes. Say, connecting AML to hypomethylating agents via a recommended for relationship, or linking elderly patients to treatment toxicity via a risk factor edge. So each relationship is assigned a confidence score, which is also stored as a property in Neo4j. So this enables probabilistic filtering and relevance weighting during traversal. So this is something that you call as probabilistic knowledge graphs, where the edge between two nodes necessarily doesn't mean that it should be true. It just assigns a confidence score and defines a possibility that the relationship might exist, and it's not a certainty. So with Neo4j's native traversal engine, the system explores relevant reasoning paths, applying breadth first or depth first search based on task needs. So it accumulates confidence as it navigates favoring stronger evidence-based relationships. So the graphs becomes more than storage. It becomes an engine of inference. So the next step is generating natural language explanations. So for each reasoning path, the system invokes an LLM to produce explanatory traces like recent trials suggesting hypomethylating agents offer a better tolerance profile in elderly AML patients with poor cytogenetics. So these kinds of explanations are transparent, grounded in evidence, and easy to audit. So the next is synthesizing the final answer. The system compiles all relevant reasoning traces into a single final response, complete with an overall confidence score. And this overall confidence score could be computed by aggregating the scores across all the reasoning paths that we have computed. And because Neo4j stores the graph in a transactionally safe, real way, everything from node addition to relationship scoring reflects the latest available knowledge and not a static snapshot. So, why Neo4j matters for this kind of adaptive KGs? So, it basically allows your KG to evolve in sync with the world. So, every update, like new research, changing guidelines, or even shifting terminology, is reflected immediately. And every AI query reasons over a live, structured, and evidence rich landscape. So, that exactly is what we called adaptive intelligence. Okay. So now let's move into how we actually keep a knowledge graph fresh and how Neo4j enables dynamic real-time updates that power adaptive AI systems. So start with this. How valuable is an AI assistant if it's working with yesterday's data or even last hour's data? In fast-moving domains like healthcare, finance, news, or e-commerce, things change constantly. New research, new regulations, new customer behavior. So Neo4j gives us a way to keep our knowledge graph continuously updated, meaning our AI is always responding based on what's happening right now, not stale or outdated snapshot. So Neo4j enables real-time ingestion using streaming tools like Apache Kafka. As new data flows in, whether that's a clinical record update, a product specification, or a breaking event, it's pushed directly into the graph as new nodes and relationships. So, crucially, Neo4j's ACID compliant transactional model makes these updates instantly queryable. So there's no nightly refresh, no indexing delay. The graph evolves in sync with the data. So a common setup uses change data capture pipelines or CDC pipelines. For instance, streaming changes from a patient database or product catalog into Kafka, which needs the Neo4j's sync connector. This connector transforms those events into Cipher query updates in real time. So, whether it's a new patient admission, a product going out of stock, or a lab result being flagged, the graph reflects it instantly without ever interrupting user queries. So, let's make that real now. Imagine you're building an AI assistant for a hospital. The backend runs on Neo4j and tracks patient data like EHR, EMR, lab data, treatments, and clinical guidelines. A new lab result arrives or a new trial paper is published, so it's straight away streamed into Neo4j. Now, when a doctor asks, what's the recommended treatment for John based on his current medication and the latest research? The system answers using the very latest state of the graph. So this isn't just static memory. Like I said, this is live intelligence. So now here's where it gets even more powerful. This graph doesn't have to be curated manually. With Neo4j's LLM-powered knowledge graph builder, you can automatically convert unstructured documents like research papers, emails, support tickets, or even EHR structured data into structured graph. So the LLM extracts entities, relationships, and context and inserts them as nodes and edges. So no cipher coding, no manual cipher coding is actually required. So you just drop in a document and the graph grows by itself. So this means your knowledge graph isn't just fresh, it's self-updating. So as new documents arrive, they're parsed, linked, and embedded semantically. So let's say relationships like treats, risk factor, and has side effect can be inferred and stored with confidence scores. Over time, your graph doesn't just grow, it gets smarter. And because it's built in Neo4j, the performance stays even fast as the volume scales. So Neo4j handles this at enterprise scale through Neo4j Aura and clustered deployments. So you get high throughput ingestion and low latency querying simultaneously. Kafka smooths the data pipeline. The graph's index-free adjacency enables fast traversal and reasoning. So this is why Neo4j is used by global leaders in healthcare, pharma, and finance. So it's proven to handle dynamic workloads while staying secure, compliant, and explainable. And that's the reason I would say Neo4j is my personal favorite graph TV. So so next we'll focus on HITL. Or let's now zoom in into a crucial pillar of adaptive KGs, the interplay between life cycle automation and human in the loop. That is HITL oversight. This balance is very vital in high stakes domains like healthcare, where AI needs to move fast but never without guardrails. So, picture this, a hospital knowledge graph that reads medical literature overnight. By morning, it has ingested new clinical trials, added notes for emerging drugs or mutations, gene mutations, and proposed relationships like drug X treats drug Y or gene A is associated with cancer Z. So this is lifecycle automation, where AI handles ingestion and enrichment autonomously. So the system parses unstructured text, extracts entities and relationships, and adds them into the Neo4j graph. But here's the twist. Not every relationship is blindly accepted. So some edges, particularly the ones involving treatment, risk, or contraindication, get flagged for expert review. Like a pharmacologist might log in and see review suggested Edge drug contraindicated in pregnancy with a confidence of 74%. So this must be inspected, the source must be inspected and either approved, rejected, or revised. So that's the human in the loop automation. Here the humans curate. So now before we go further, let's tackle a key question. Where do these confidence scores actually arise from? In Neo4j powered adaptive KGs, each relationship is assigned a confidence score. So a numeric estimate of how trustworthy it is. So these scores are based on multiple signals. First, the LLM's own certainty, like how confidently it predicted the relationship. Or second, it can come from independent sources that support the claim, like more evidence means more trust. And third, it could be based on the clarity and quality of the reasoning trace. If the system can explain its logic cleanly, that's a very good sign, I would say. Fourth, it can be based on citations from trusted sources like PubMed or official guidelines that boost credibility. Fifth, let's say the recurrence of the relationship. If it's inferred repeatedly over time, the confidence also grows. And lastly, domain specific logic. For example, a fact from an FDA label might start at 95% confidence, while an anecdotal forum post might, let's say start at 60% score. So these scores are saved directly as properties on each relationship in Neo4j and used downstream for triage. A typical thresholding strategy might look like this. Any fact with confidence above zero point 0.9 goes straight into the graph. And let's say something between zero point 0.7 to zero point 0.9 is flagged for human review, and below zero point 0.7 is just held back. So this ensures we don't slow things down unnecessarily, but we also don't let questionable facts slip through. So let's walk through a real example. Suppose the system infers drug Z is contraindicated in condition Q, but the confidence is only 75% based on a single case report. The edge is added provisionally but flagged for review. An oncologist logs in and checks the context and realizes that it's too weak, just one patient and no generalizable evidence. So he or she clicks reject. The edge is removed from the graph and the system logs that decision. That rejection becomes a training signal. The AI learns to treat single case reports more cautiously. On the flip side, if the evidence were strong and the doctor approved it, the relationship would become a trusted, validated edge, and that approval gets noted too. So, this is the real power of HITL systems. Each correction teaches the model. It's not just review, it's active learning. The system gets smarter every time a human weighs in. Over time, the LLM proposes better relationships, and experts have to intervene less often. Some systems even fine tune their models periodically based on these feedback loops, turning expert oversight into model evolution. So now to make this scale in production, a few best practices are efficient. First, let's say clearly mark machine generated facts in the UI, maybe a color coded edge or an icon that says AI suggested. Let reviewers see the reasoning trace, like what sources and logic led to this suggestion. Second, we could log every edit, who approved what and why for compliance purposes, especially in healthcare and regulatory industries. Third, we could streamline the review process. Give experts daily batches of 10 to 20 edges to approve with a single click per item. And the fourth could be define clear governance. Which edges must be reviewed? For example, any contraindication or risk related relationship should always pass through a human, like I mentioned before. But routine associations with confidence might skip review entirely also. Hence, This HITL workflow is not optional in domains like medicine. A knowledge graph that powers clinical decision support must be almost error-free. The stakes are simply too high to go fully autonomous, but this is true beyond healthcare. The same principles apply in finance, law, e-commerce, and even support. So in finance, a flagged fraud relationship might be reviewed by compliance. In law, a precedent link gets verified by an attorney. And in support, let's say, a suggested answer is edited by a human before it goes public. So the pattern is clear. Let automation scale the graph and let experts shape its integrity. Neo4j makes this possible by capturing both the structure of the relationships and the metadata needed to score, audit, and evolve them. So the result is not just a knowledge graph, but it's a living, learning, and trustworthy systems. So thank you so much for attending this session. And I really, really hope that you all get to use adaptive gauges in your own fields of domain, fields of interest. And also, I would like to mention that I'm coming up with a LinkedIn Learning course on Introduction to Probabilistic Knowledge Graphs, like defining probabilistic models over nodes and edges, and performing inferencing over them using MCMC and then nuts inferencing. So I hope you all get to explore that course, and I would be more than willing to connect with you all on LinkedIn and get your feedback on it. Thank you so much.